Hello, everyone. My name is Yaron Schneider. I work at Microsoft, and I am a Dapr core maintainer. And with me is Aman Bhardwaj, who's going to introduce himself.
Hi, this is Aman, and I work at Microsoft and work on Dapper project with Yaron as a core maintainer for it.
Yeah, and today we're going to be talking to you about stateless functions and stateful actors. So before we start talking about any sort of solution, let's talk about cloud-native developers and some of the challenges that cloud-native developers face today. So developers are being asked to write very resilient, scalable microservices-based applications that mostly interact with other services, whether it's through direct service-to-service invocation or whether it's event-driven. And those types of applications have multiple languages that they're written in. So they're becoming increasingly polyglot. And that's also a challenge because you sometimes need to also leverage existing code, introduce new code to the mix, and new languages need different SDKs. And those stuff basically have developers focus on things other than their core business logic, like infrastructure. And then we have things like functions and workflows and actors, which we're going to talk about, which really represent very powerful stateful programming models and stateless programming models, but each of them have their own specific challenges. So really, a few things that are holding microservices back are having to incrementally migrate your existing code to a microservices architecture. You need to deliver in your business logic, and then you want to leverage the strengths of the microservices architecture, but you don't want to rewrite your entire code base. So you go onto these new programming model runtimes, but they have narrow language support. Some of them are bound to one cloud provider or another. They have very tightly controlled feature sets, which really have you tie into a very specific way in which you need to write your code. And some of them only run on specific infrastructures, and they're not that portable, between the cloud and the edge. And we're seeing more and more code being transferred to the edge. So we introduced Dapr to allow developers to solve these hard problems of distributed applications. And Dapr really, you can think about it as a runtime that runs as a sidecar to your applications that gives developers sort of superpowers, just the same way that Kubernetes and a lot of other infrastructure-oriented projects give developers and operators the ability to run distributed apps at scale. With containers, Dapr really appeals more to the developer side of things and give developers APIs that help them focus on their business logic. Some of the core goals of Dapr are, first of all, to give developers best practice building blocks, meaning all the best practices that you can find in distributed systems are basically built into this sidecar. So whether you're doing stateful operations or pub sub or service invocation or any of the other features that Dapr gives you, we make sure that they're due to best practices and that Dapr really solves those hard problems. And then the second type of goal that we have is to be language or framework independent, meaning be as inclusive as possible to all developers out there, no matter which language you're using or which framework, Dapr supports it. And then being consistent and portable so that you can take your code and port it over to different environments. We also want to adopt standards where we can. So things like W3C trace headers and standards, other standards that you can find inside of the CNCF ecosystem are being leveraged by Dapr. Extensible and pluggable components is also something we give great care for, so that you can plug in different components so that you do not need to tie yourself into any specific underlying implementation. And then being platform agnostic for cloud and edge, meaning you can take your code and port it from one environment to the other, whether you're running on AWS, Google Cloud, Microsoft Azure, or the edge. Then maybe even the most important thing is to be community-driven and vendor-neutral, which is critical to Dapr to increase its adoption and really make sure that people coming from different companies can collaborate on this project with us. So what is Dapr really? We can see our application code here at the top, meaning if you're a developer, you can write your code in any code in any language, really, or use any framework. So it can be Node, Go, Python, Java, Rust, C++, whatever you're using. You can talk to Dapr, because Dapr is a sidecar that exposes APIs for developers with HTTP and gRPC. So any type of programming language that comes in tomorrow even will be able to leverage Dapr using its native APIs. Some of the capabilities that Dapr gives are really called building blocks, which you can see here inside of the Dapr block. So service-to-service invocation is the ability to find a different service in the cluster using a unique ID and really get abstracted away from all of the service discovery and reverse proxying mechanisms. Dapr will do discovery for you, it'll do retries, and it'll build in resiliency into your calls. State management is another kind of building block that we have, which really gives you very nice abstractions over state management. So as a developer, you can write your code once and target a key value API and then plug in different components. So for example, if you're running on AWS, you can just configure it to use DynamoDB. Then if you're running on Azure, for example, Cosmos DB, and if you're running on-prem, it can be Cassandra, Redis, or any one of the other components that are supported by Dapr. PubSub is the ability to do a publish-subscribe type of event-driven scenario, where you have publishers asynchronously send events to consumers that might or might not be listening at the moment where the message was sent. Resource bindings and triggers allow you to trigger your application whenever an event comes in from an external system. Think like a Twilio message, or even a Twitter tweet that comes along, or an Event Hubs message, or AWS Kinesis messages. And then, just like you can trigger your application based on that code, you can also invoke other systems using those bindings. So your application can tell Dapr, hey, take this piece of data and send it to that particular binding. Actors are really a special programming model that encapsulates compute and state together. And we're going to touch specifically on actors during these slides. Observability is you getting distributed tracing for free with Dapr. Because you talk to the Dapr APIs, Dapr knows to talk the language of Open Census and the protocols of Open Telemetry, and it'll inject headers into the calls and create really this application map for you, where you can have end-to-end visibility across the calls into your applications and from your applications. Secrets are a really nice thing. Think about, your pod running in the Kubernetes cluster, and you need to extract secrets from HashiCorp Vault or the Kubernetes secret store, and you don't want to start mounting stuff on the pod. So Dapr has a really easy API where developers can just call secrets and get them back. And then everything else is really extensible. Those building blocks and the components that they use are really pluggable. And there is actually a separate repository under the Dapr organization in which community members can contribute more and more components. And then all of this runs on cloud or on the edge. So Dapr does not have to run in a container. That's important. It can also run just as a process on your machine. So you get a really lean development experience running Dapr on your machine, whether it's Mac, Windows, or Linux. And then taking that thing and running it on Kubernetes is really not that different from running it locally. This is Dapr hosted on Kubernetes. So Dapr, like a service mesh, really injects a sidecar container into your pod. So you have your application pod here, your application container inside the pod, and you have the Dapr container being injected. And because they're running under the same network namespace, your application code in the container just talks via localhost to Dapr. So think about it like having a special friend in localhost that does things like state management and PubSub and service invocation and tracing and secret extraction for you. Dapr is really, really lightweight. It uses 4 megabytes of RAM, of committed memory. It's a 23 megabytes image. Its container image size is smaller than Envoy and the Linkerd proxy, I think. And it uses only 4 system pods. So we have the sidecar injector, which is really lightweight. And we have a certificate authority called Sentry, which gives you end-to-end encryption. It does MTLS for you, much like a service mesh. And then we have an operator, which updates the Dapr sidecars whenever an operator or developer changes their components. And if you're using the actors building block, we also have a pod for doing the actor placement, which really decides where each one of the actor compute units are located inside the cluster. So Dapper and service meshes. Dapper can utilize any service meshes, and Aman can elaborate on that.
Yeah, so one idea for Dapper is that it takes more of an additive approach, and it doesn't preclude service developers from using any of the existing cloud native technologies. So in this slide, you can see that Dapper runs in the same pod with the user application and the Linkerd. And because Dapper runs at an application level and service meshes run at more of a layer 4 level, so they all can coexist in the same pod and provide additive capabilities to the user applications.
Yes. So like Aman said, service meshes really work at the network level where they intercept traffic, and Dapper is more of an application level concern. There are some overlaps with mutual TLS and tracing, but everything in Dapper is also configurable, so you can turn it off or on based on whether or not you're running a service mesh. So Dapper plays really well with things like Istio and Linkerd. Another CNCF project that Dapper really integrates well with is CADA, the Kubernetes event-driven autoscaler. So because Dapper supports a very wide range of components, a lot of them overlap with CADA, which means that you can use CADA to autoscale your Dapper instances.
So this slide shows the service invocation building block for Dapper. Service invocation provides the capabilities to developers to directly invoke their service methods without worrying about service discovery on a particular platform. So using Dapper, services are deployed using an ID, and after that, one service can talk to another service using that Dapper service ID. So in this example, you can see the front end is trying to make a call to this backend card service, and it just does that over an HTTP post request to its Dapper sidecar, and it says that I want to talk to this card service, and this is the method checkout which I want to invoke. And so the call goes from front end to its Dapper sidecar. Dapper sidecar figures out where is the target service running. It forwards the call to the target service's sidecar, and it lands on the target service. And the response comes back to the front end using the same route. This is the service invocation capabilities for Dapper. Now moving on to observability, Dapper provides certain building blocks for observability like metrics, traces, and logs, so that service operators can look at the health and metrics coming out from the Dapper system services or the system pods to get more insight into what is going inside the Dapper sidecars. And Dapper integrates currently with Open Sensors. In future, we will integrate with Open Telemetry so that metrics and logs coming out of Dapper sidecar can be viewed with any of the open source tools available like Jaeger or Datadog and Azure Application Insights as well.
And this is state management for Dapper. So, for example, an application can talk to the Dapper API, and this is quite a simplistic view of a stateful operation that Dapper does. So it supports a key value API model at the moment, where the application basically says, hey, I want to save two objects, and they both have keys. So we have Star Wars themes examples here because we all have Star Wars in Dapper. And then we're basically saving two pairs of keys and their values. So the value can be a primitive, or it can even be a complex value. And then Dapper, based on the state store that you configured it to work with, will make sure that the state gets written. And Dapper also supports some other advanced capabilities on top of those basic primitives. For example, you can choose between a first write wins and a last write wins model, or you can choose between eventual and strong consistency. And Dapper has those capabilities on top of state stores that might not even natively support those. So those are really powerful features. And for each one of the Dapper building blocks, Dapper has more features that it provides on top of the base implementations that it hooks up into. Similarly, this is a get statement. where we saved some state, and then we're calling Dapper, the HTTP API, to get the state back. It's also important to know that all of those calls are available via gRPC as well, and not just HTTP. And we also have some SDKs on top. But really, the lowest common denominator in terms of protocols are HTTP, so that we're inclusive to all developers out there. Now, those are some examples of the Dapper building blocks. We're going to talk about actors next. We can't go into all of the building blocks here, but we encourage you to check all of them out inside the Dapper repository. So before we move on to actors, this is, for example, what a map of our application for tracing would look like inside the cluster. So you get tracing basically for free with Dapper. You just set up your tracing backend, configure it with a simple YAML, and then Dapper will show you the map for your application calls. What's nice about it is that unlike a service mesh, which really traces between request-response types of invocations, Dapper will also hook up your event-driven messages that are coming through external systems that might not go through the service mesh. So that's kind of nice.
Okay, so the next we talk about the actors building block for Dapper. Actor pattern is a computational model for concurrent or distributed systems, in which a large number of these actors can execute simultaneously and independently of each other. Actors can communicate with each other, and they can create more actors. One thing which is unique about actors is that they are single-threaded, so one actor method can execute at any given particular amount of time. So till now, actors existed in their own language frameworks, like Akka for Java and Akka.NET is the .NET equivalent for it. And then there are other reliable actor patterns available, like Orleans and service fabric actors. What Dapper does is it encapsulates the core functionalities of an actor framework in the Dapper sidecar, like turn-based concurrency, actors, timers, reminders, and state management, and distribution and failover, so that users can write their actor services in any language of their choice. They just need to talk to Dapper sidecar over HTTP or gRPC, and Dapper will take care of all the core functionalities of an actor system. And Dapper can scale up or scale down your actor instances as and when you scale up or down your services. So Dapper has a placement service which takes care of distributing your actor instances across multiple parts of your service. And as they come up and down, Dapper will redistribute their actor instances across these parts. It's a very powerful programming model for IoT devices and distributed systems.
Yes, so we can actually, if you think of drones, for example, you could model a drone as a pod, and then you'd have, maybe if you have 1,000 drones, you'll have 1,000 pods. But with actors, you can actually host millions of actors inside of a single container, which is really powerful, really. Okay, let's stop talking now and show some demos. So I'm going to be sharing my screen. Okay, and here we have Visual Studio Code, and we're going to see a very simple demo about running Dapper locally and then on Kubernetes with binding. So let's say I'm a Node.js developer and I want to start getting events coming in from Kafka. So this is my Node app here, and this is extremely simple. As you can see, it's just Node.js. My application code is very lean, no SDKs, no libraries, nothing here really. All we have is a simple web server that listens to some endpoint called sample topic, and then we're printing hello from Kafka and the body, and just sending back a 200 response. What could be simpler than that? Really, I'm not tying into any FAS. This can be a long-running type of application. So this really meets me as a developer where I am. And so I'm listening to sample topic here, and the only thing as a developer that I need to do to start getting events is just write this really simple Dapper component, which is a CRD, but also works outside of Kubernetes. And here we have the name sample topic, which is the endpoint that we're listening on here. And here we have some metadata about how to connect to Kafka and some configuration options. So I will go over here to my terminal with my Node app, and I'm going to use the Dapr CLI to allow me to run both the Dapr sidecar and my applications. This is a developer-facing tool that's really good for the inner dev loop stage. So I'm doing Dapr run, and I'm giving my application an ID here, and I'm telling Dapr which port my application is listening on, and then I'm just launching my Node application. So this will launch Dapr runtime and my application side by side. So we can see that we're running, and we have both the Dapr logs and the application logs written to the same session window. And I'm going to do the same thing here for the Python app. And the Python app is currently sending events to Kafka also through Dapr. And we can see this here, really simple Python application. And we can see that this has the Dapr URL here. So the Python application is just having a really simple loop, and it's calling Dapr on localhost, calling bindings, and calling the sample topic name. So the Python app also has this YAML that we saw before, and it's sending a very simple payload. So a very simple, SDK-less Python app sending messages to a very slim Node.js application. If we go back here, we can see that we are getting the responses back. Now, let's say we want to deploy this thing to Kubernetes. We've already containerized our applications. So we have the same CRD, which we're going to deploy to Kubernetes. And here we have Kubernetes manifests. So this is a regular Kubernetes deployment. And the only thing we need to do is annotate the deployment and say, hey, we want to Dapr enable it. And then Dapr will inject the sidecar into our pods. So we have the same for the Node.js and the Python application, a really simple configuration. So the way to get started with Dapr really is you can install it with Helm on Kubernetes, but if you just want to install it in a dev test mode, you can do Dapr init -- Kubernetes, and that'll install Dapr onto our cluster. And so we can see that it's already running. And if we take a look at the pods, and we'll wait for them to come up, and everything seems to be up and running, and we can use the Dapr CLI. See that we have the latest version of Dapr running, and the control plane is healthy. So that's all it takes, really. Now, the only second step is to deploy everything onto our Kubernetes cluster. So we're in the deployment folder here. So I'm going to deploy the Python app, the Node app, and the bindings for Kafka. And while this is deploying, we can see that we have Kafka installed inside of our Kafka namespace. And if we take a look at the pods that we have here, we can see that the Dapr pods are running, and our two apps are running too. So we have two containers inside our pods, one for the Dapr sidecar and the other for the user app. And now if we take a look at the logs for the Node app, we can see that the same code that was written on our machine just got containerized, and it's talking to Kafka. And if we take a look at our components, we can see we have our sample topic component here. And now I can just switch this sample topic to be, for example, instead of Kafka, it can be RabbitMQ or any other of the supported Dapr components. And then without changing anything in my code, I just get events coming in from the system that I configured to work with Dapr. So I'm going to be transitioning over to Aman. I am stopping my screen share here.
Okay, let me start sharing my screen now. Okay, is it visible now?
Yes,
okay.
It is.
Okay, sounds good. So I'm going to demo the next two building blocks for Dapr. One of them is actors. So Dapr provides first-class support for language SDKs to write your actor applications. This is an example using C# SDK, but we have language SDKs available for Java and Python, and more are on the way. So in C# you would write your actor by writing an interface which contains methods for your actors. In this case, it's called idemo actor, and it contains two methods, save data and get data. If we look at the actual actor implementation, you just define your class demo actor, deriving from our base class and implementing the methods inside this idemo actor. If we look at the methods called save data and get data, you can see that save data is interacting with the state manager to save the state. And then it's using state manager again in the get data method to get the state. So what it's doing behind the scenes is that it's making calls to the Dapr sidecar to save the state using the configured state store for Dapr. And to configure a state store, it's the familiar component YAML. It just says that use Redis as the state store for actors, and Dapr sidecar will start using it. Now, how to make calls to your actor service from a client service? It's pretty simple. You just create an actor proxy and tell it that you want to talk to an actor ID, and you make a call to a particular method. In this case, it's making calls to save data and to get data. And to run this service, you integrate with ASP.NET Core. While creating your web host builder, you just say .use actors and then you register your actor type. This will configure the actor SDK runtime to talk to Dapr sidecar and bring the whole functionality of actors to you. Now let's try to run this, and we'll run this using our Dapr CLI. It's just saying Dapr run, port is 3500 for Dapr, application port is 5000, and then it's going to just run the actor service. So once the actor service is running, you can run the client application, which I just showed you. It's just going to make the calls to actor sidecar, actor service using the Dapr sidecar, and then invoking those two methods. As these actor services can be written in any language, so Dapr allows for cross language invocation. So in this case, I'm going to show you invocation of the actor method using HTTP. This could be any language of your choice. So it's going to make a call to local Dapr sidecar over port 3500, and it's saying that invoke this save data method for demo actor type, and the actor ID is ABC. And once it does that, it's going to save the state into the actor using Dapr sidecar, and then you can query the state using the get data method here. So it's going to query the state back from the actor sidecar. So the next building block I'm going to show you is PubSub from Dapr. With PubSub, you can have your application subscribe to a topic, and other application publish emails to that topic, and your subscriber will get notified. So in this example, we have a very simple Node.js application. It's just telling Dapr, hey, I'm interested in topic A and topic B, and these are the routes on which you should invoke me whenever there is an event for that topic. Similarly, there could be a Python application. In this case, it's a Python application telling Dapr, hey, I'm interested in topic A and C, and these are the routes on which you should invoke me whenever you see a message for those topics. Now let's run this node subscriber using Dapr sidecar, using Dapr CLI, and then run the Python subscriber using Dapr CLI. Now to send messages to these topics, I have a very simple React form application, which is going to send topics to, which is going to send emails to these topics. Let's take a look at this this server application, which is publishing the events. To publish the events using Dapr, you just make an HTTP call to this publish endpoint, and then you give it a topic name and the body of your message, and it will be sent to the Dapr sidecar, which it will in turn invoke your subscriber applications. So this is the web front end for the React form. I'm just gonna send a test message to this topic A. So this goes to the React form. It publishes the message using its own Dapr sidecar. So if we go back to our Python subscriber and Node subscriber, you can see that they both have received the messages for topic A. This is the Node subscriber, and this is the Python subscriber. That's all from my side.
All right. So stop sharing and go back to the slides.
Yep.
Okay. And so we invite you to join the Dapr community over on GitHub, Gitter, YouTube. We're pretty much everywhere. Just join us, open issues, download the software, try it, and keep in touch with us. We really want to onboard as many developers as we can to Dapr, and with your help, have it really solve all the problems of distributed computing. We'll open it up for questions now. Thank you all.
Thank you. So you're available in a solution with strict latency requirements, and is HTTP or gRPC calls to a sidecar on localhost going to be concerned?
Yeah, it's a good question. So for that, we are going to release performance benchmarks for Dapper pretty soon, so we'll know the exact latency and processing added latencies for Dapper. If you were just having your application, for example, publish a message or go to another app directly or through Dapper. We know today that the network cost of calling into Dapper is about 600 microseconds. And we can also share that under a load of 1,000 requests per second with a 1 kilobyte payload, the Dapr sidecar will add 4.2 milliseconds end-to-end network latency, meaning the application calls to Dapr, Dapr calls to Dapr on another VM, so a network hop, and then Dapr calls into the second app and all the way back. So it really, the answer is it depends on your latency requirements, but what we're seeing so far is pretty good.
Cool. Thanks, Yaron.
So then,
could you please provide a guidance, provide a glimpse of what Dapper needs to know about its backends? Say Dapper needs to understand that backend access transaction or two-phase commits. So basically discovering the capabilities of the component that it's just talking to.
Okay. Liam, can we still access native APIs with services like Kafka, or we're limited by the interface? You're limited by the interface, but Dapper provides sort of escape hatches into specific features. So if you actually go on our repositories and take a look at the specifications that we have for the different components, you'll see that it's very easy to add very feature-specific stuff. So you don't have this lowest common denominator stuff. Do you have plans for actor relationships or topologies? Aman, you probably want to take this one?
Yes. Yeah. So Dapper follows the virtual actor model coming from Orleans or service fabric reliable actors. So you should be able to create actors from within actors that can give you sort of a child-parent relationship there.
What is the governance model of Dapper? That's a very good question. So currently, we're actually building a governance model now, which we're going to announce in the next, I want to say the next month, at least announce the plans for it. But if you check out the Dapper announcement blog from October of 2019, we made a commitment for open governance and to donate Dapper to a foundation. So that's something that we announced, and we intend to follow up on that.
So I think the next question is, does Dapper have in-memory store, say, for local development testing? So for local development, Dapper CLI, when you do Dapper init, it sets up your local development environment, and it sets up a local Redis instance running in a Docker container, which can be used for local testing in your dev environments.
When can we expect a 1.0 release? Yeah, that question comes up a lot. By the end of the year, calendar year. So yeah, we're shooting for, I would say, the October-November timeframe, something like that. Everything's open. If you go to the Dapr organization page, you will see projects. You will see the milestones. Anything that's marked as P1 needs to be done before the 1.0 release. So it's all it's all out there. And again, we'd love for you to come and help us, because the sooner we get those items done, the sooner we can get to 1.0. And so far, we've seen an amazing participation from the community. So we need to start wrapping up. We will be on the serverless Slack channel to continue the discussions. We'd love to talk to all of you there. Yeah, so if there's not any more questions, we can wrap it up there. Thank you all. Thank you for watching, and thank you for participating.
Thanks, everyone.